Hello and welcome to Sam-Splaining Science. I'm Sam, I'm your host. I'll be Sam-Splaining the science, and today we're talking about aging because I'm getting older too. That's a reference to Fleetwood Mac, for the record. Show of hands, who here has recently cried their eyes out listening to Landslide? Anyone? Just me? Okay. Well, honestly, therapeutic experience, 10 out of 10 would recommend. This episode is about aging, as I said. It was supposed to go out July 29th because my birthday was July 28th. And I thought, how nice would it be to talk about aging the day after I get a year older? But life happens. Technical difficulties happen. And now I'm recording this in August. Whoops. But it's never too late to learn, so we're learning about it now. I don't know if you've noticed, but I have gotten older since the last episode. I'm a full year older, even though the last episode was only like 3 weeks ago, something like that. But I'm 31 now, which is crazy. I'm officially in my 30s, which 30 doesn't count as your 30s, right? Like the decade year doesn't count. Last year I was 30. This year I'm in my 30s. It's different. And I might sound crazy for saying that, but I don't think it's that crazy. I think it makes sense to me. But because it was around my birthday when I was planning this episode, I figured it would be good to have an episode about aging and senescence. Humans typically live, like the life expectancy for humans is like mid 70s to 80s. And I did the math and I'm about 40% of the way there, which, What? 40%? That's scary. But then I also looked it up, and the longest living person lived to be 122 years old. So I'm going to choose that statistic because in that case, I'm only like 25% of the way there. I like that one better. So I'm going to go off of that one. I expect to live to 122, maybe 123 and beat the record. We'll see. Knock wood. God willing. But yeah, this episode is about aging, and last episode about the tattoos was I think one of the longest episodes I ever had, which is crazy. So I'm going to try to keep this one short. You know me. I'm a yapper. I'm a certified yapper. I could, especially about science, please. I can yap all day. But I'm going to try not to. I'm going to keep it under. My goal is to keep it under 40 minutes. So, chip, chop, chip. Okay, here we go. Let's get into today's. Anyway, before I get into the questions, though, I hope you're well. Thanks for tuning in. How are you? I hope you're good. Okay, pleasantries over. Let's get into the questions. Oh, for the love of all things good and holy. There we go. Okay. So today's questions, I have 2 questions today. The first is, what causes aging? Like, why am I aging? Why? And the second question is, why is my hair turning gray? Because I don't think it's very obvious right now in the video. Also, my hair's kind of wet still because I washed it this morning. But I've got some grays going on. I've got little specks of gray here and there. And I'm like, why does that happen? And why does that happen as we get older? You know, it's kind of weird. So I looked up the answers as to why hair turns gray. And spoiler alert, I didn't do vocal warm-ups today. Vocal warm-ups, like I'm a freaking opera singer. Usually I do some like that sort of shit to like wake up my speech, the sounds of my face. I don't know what I'm saying. I didn't do that today. And now I'm stumbling and bumbling like a hot mess, but you knew that. You knew that I'm a hot mess. But anyway, I looked up the reasons as to why our hair turns gray, and spoiler alert, it's not because we're not God's favorite. there's actually like some hypotheses as to why on a cellular level it happens. And that has nothing to do with God hating me. So that just must be the other shit. Just kidding. Kind of. Okay, anyway, first question. What causes aging? So I looked up, like when I was doing the research for this episode, I looked up aging. And one of the things that was written was like, aging is a consequence of time. And I'm like, isn't that the truth? Aging is a consequence of time. I love how brutally honest and accurate that is. But other than it being a consequence of time, thinking about aging, I wanted to kind of go into a cellular level approach of what causes aging, because our cells get older with time, but our cells make up our tissues, and our tissues make up our organs. Like when you think about getting older, you think about your skin getting wrinkly and your hair turning gray, which we'll talk about. And you might think about, maybe your bones getting more brittle, or your muscles getting weaker, or, maybe your brain working differently than it used to. And it's just like all of our organs function changes. And I think when I think about that, I think about it at like the cellular level. What's happening in like the building blocks that's making the organ not work the way that it should. So for a lot of this episode, we're going to be talking about cells. So I hope you remember your 8th grade biology. Just kidding. We'll talk about what we need to know. Don't you worry. I'm not leaving you in the dust like that. No way. But yeah, I think I took it from the approach of starting with cells. And specifically, what causes aging, what can cause aging, one of many things that can cause aging in our cells is oxidative damage. So the theory here is that metabolism may be contributing to aging, or in other words, aging is a byproduct of metabolism. So metabolism, you might be saying, what the fuck does that mean? Sorry, I really try not to swear, but then sometimes it slips. I'm not going to go back and bleep it. This is not a children's show, for the record. I'm not child friendly. My language, not child friendly. As a person, I'm child friendly, but as a speaker, no. Unless you want your kids to swear, in which case I'm fine. But I guess that's up to you how you want to raise your children. That's none of my business. Anyway. Sorry, got to have my iced latte. Gets me through life. Okay. So metabolism, you might be saying, what the heck is metabolism? Metabolism is a process that goes on inside of our cells that takes glucose or sugar and oxygen and does a bunch of reactions to turn that into energy that our cells can use to maintain function. And it also has byproducts of water and carbon dioxide. One of the processes, one of those reactions that takes glucose and oxygen into energy, water, and carbon dioxide is called oxidation. And this is a process that happens within the cell, partially within the cell, in the space within the cell, which is called the cytoplasm. It's basically like fluid inside the cell. But then it also happens within the mitochondria, which you might remember is the powerhouse of the cell. She is the backbone of the cell because she makes a lot of energy for the cell to do its thing. So the oxidation step happens in the mitochondria. And this is essentially where the oxygen and the glucose byproducts undergo these reactions to make a lot of energy. And sometimes that process of oxidation in the mitochondria, it is not 100% efficient. It is not perfect. What is perfect in this life? Am I right? But sometimes it's not efficient, it's not perfect, and it creates what's called a reactive oxygen species, or an ROS. And ROSs, reactive oxygen species, can oxidize and really just damage things in the body, in the cells, right? So it can damage proteins, it can damage nucleic acids, which build up our genome and our DNA. And it can even damage cell membranes, which are the things that kind of keep the cell and all the fluid inside the cell together. So if that gets damaged, it can cause the cell to burst and die. So the theory, if we're thinking about oxidative damage contributing to cell aging and just overall aging, the reactive oxygen species can cause damage that can cause damage to the cells that can then lead to improper function of the cell, which can then lead to improper function of the organ, right? So the theory is that, like, over time, this happens more and more frequently. So that will contribute to more and more damage over time. And if that's the case, then maybe if we can destroy these reactive oxygen species or prevent them from being created in the first place, maybe we can prolong life if they are the things that are causing aging and causing dysfunction of cells and organs. And there's actually some evidence for this in Drosophila, which are flies, and C. elegans, which are little worms. So there are types of these flies and worms that have enzymes or chemicals in them that can destroy reactive oxygen species. And the flies and the worms that have these enzymes that kill the ROS actually end up living longer. So that kind of supports the hypothesis here that if we destroy the ROS, we can live longer. However, evidence for this in mammals, like in humans and other animals, like mouse models or rodents, that's not as clear. There are some evidence. There is some evidence. There are some evidence. English is my first and only language, for the record. Thank you. There is some evidence in humans that can suggest that oxidative damage leads to aging. And in particular, it really points to increased metabolism that leads to aging. And then it's assumed that with that increased metabolism comes increased oxidative damage. So, for example, there was a study in mammals that showed that caloric restriction led to slower metabolism. And that in turn led to prolonging the life of I think it was in mice. I should double check that. But essentially, and that kind of makes sense, right? Because if you have less glucose in your system, assuming that you restrict your calories and you have less of it in your system, then you'll have less for metabolism. And then if you metabolize less glucose, then you have a fewer chance of oxidative damage because of the slower metabolism. But I don't know about you, but I'm like, I would rather eat good than live longer. I'm here for a good time, not a long time, you know? But I don't know. I feel like that's not really, like, I read that and I'm like, okay, I'd rather die than that's so dramatic. But you know what I'm saying, right? Like, caloric restriction, like, how much can it really help you live longer? Come on. Is it worth it? If it's like, oh, if you restrict your calories to X amount, you can live an extra 5 years. I'm good. I promise you, I'm good. But you do you. So that's also just to say that I think the exact mechanism by which that actually happens and which could actually prolong your life is not well characterized. So don't put your money on that. Don't restrict your calories to try to live longer, in my opinion. But again, I'm not a health expert, so what the fuck do I know? I'm not a dietitian. I'm not an expert on aging. I'm just somebody who's getting older and someone who likes food. So I'm like, you know what? If I'm going to age anyway, might as well have a pizza. Might as well. Okay. Sam, come on. You want to keep this quick. Okay. So vitamins C and E have also been shown to potentially be ROS inhibitors in flies and worms as well. Actually in nematodes, which I had to Google what a nematode was because I only knew it from SpongeBob. And it turns out, remember the episode? You know what I'm talking about. The episode where the nematodes eat SpongeBob's house. Their nematodes are in fact little worms. I don't know if they eat pineapples under the sea, but they are little worms as they were depicted in SpongeBob SquarePants. So we love the scientific accuracy to a degree in SpongeBob SquarePants. Okay, anyway, in nematodes, they found that higher levels of vitamin E increased longevity. And vitamin E is a known inhibitor of reactive oxygen species. So that's sort of like, it's harder to study in mammals, but here in like these more simple organisms like worms, you can control the amount of vitamin E and determine the effect of vitamin E on longevity. It's also, I should have mentioned earlier, but like flies, nematodes, like C. elegans, all that stuff, their lifespans are much shorter. So it's much easier to study the lifespan of a fly. I meant to look this up. I think it's either 3 months or 3 weeks. Something 3 for sure. I'm Googling right now. Google. Lifespan of Drosophila. I'm pretty sure it's 3 months. Nope. 3 weeks. Well, no. I was right, 3 months. Drosophila melanogaster, which I think is the species, the genus species that's used a lot in science, has a median lifespan of 80 days. That's 3 months, right? Ish. Anyway, the point being that their entire lifespan is much more condensed than the human, so it's much easier to study. They're also more simple organisms, so it's easier to study aging in these models of aging compared to humans, which it takes us a long time to age. Not that long, though. 31 years flew by. Just saying. But anyway, there are additional causes to aging besides oxidative damage that I don't want to get too deep into the woods here. But in addition to oxidative aging or oxidative damage that causes aging, there are a lot of theories talking about a general wear and tear or genetic instability that comes with time. And more specifically here, we're talking about wear and tear and instability of our genes. So it kind of makes sense that our genes play a role in aging because our genes really define us. And like a lot of things are encoded in our genes, like when we grow, how we grow, when to stop growing. Like our genes play a big role in that. So it makes sense that it would also play a role in like when we start to age and how we age and what happens when we age. So there's a lot of interest in genetics and aging. And before I get into too many of the specifics, just a reminder that our genes, our genetic information, is made up of DNA or deoxyribonucleic acid. It has a spiral, like 2 strands that are kind of twisted into a spiral. You've seen the DNA emoji, I'm sure of it. That's pretty much what it is. It's just like a twisted double helix, it's called. And with that, there are nucleic acids that make up those latter rungs, if you will. And those are unique to each one of us. The like pattern of those pairs is unique to every one of us, and it defines everything that we are, and everything, well, not everything that we are. There are some things that are environmentally and situationally unique to each one of us, but much of what we become is based on our genetic information. And every time, or I guess I should say also the sequence of the base pairs of the ladder rungs is essentially used as a recipe to make proteins. And I've gone through this before in an episode. I'm pretty sure it was one of the COVID episodes where I was talking about the viral genetic information. Our genetic information, similarly, is used to code for proteins. So our genetic information, our DNA, is essentially a recipe that can be used to bake a protein of some sort. Every time a cell replicates, which is a lot, our cells replicate a lot depending on the type of cell. But even in the last episode, we talked about skin and how the basal cell layer of the epidermis is constantly creating new cells and like pushing the old cells up. So like every time new cells are created and cells are dividing, our genetic information has to duplicate. The genetic information duplicates and then the cell splits so that the result is two cells with identical genetic information to each other and to what the cell was before. That's a process called mitosis. And sometimes during mitosis, when the genetic information is being duplicated, a mutation can happen. And a mutation is when there's a change in the genetic sequence, when there's a change in the recipe. And the big picture here from the genetic instability hypothesis to aging is that the more times a cell duplicates its genetic information, the more likely it becomes that there will be genetic damage to the daughter cells, to the cells that come after the duplication of the genetic information. So, and then with that, these mutations, these changes can lead to problems. So like, let's just say the DNA is the recipe, right? If I'm copying down the recipe from a recipe book, but I write 1 teaspoon of salt instead of 1 teaspoon of sugar, then the whole recipe could come out differently, right? Sometimes it doesn't matter so much, but sometimes it matters a lot. And that's sort of the hypothesis that the more times you're copying the recipe, the more room there is for error. And then that error can be catastrophic to the health or the productivity of the cell. And that's sort of the thought process here, is that the more that you duplicate, the more room there is for error. If there is an error, the cell could not work properly. It could die. It could cause chaos. And that can lead to the instability of the organ as a whole, if enough cells do that over time. There are a couple more specifics, but I don't know if I'll go into it now. I don't think I'm going to. But that's all just to say that another point, actually, I guess to tie the previous point into this one, is that those ROS, the reactive oxygen species, can cause damage to the DNA as it's being duplicated, right? So like that's something that could potentially cause a mutation. So it's not like just, sometimes it is just like accidental bad copies of the DNA, but sometimes an external factor like a reactive oxygen species can screw up the DNA that's being duplicated, and then it can cause problems. So this is sort of a recurring theme, I guess, in aging, is this idea of like cellular damage, more specifically damage to the DNA or damage to the cell structure or the proteins within the cell by the reactive oxygen species. Yeah, there's some other hypotheses as well, thinking about like telomere shortening, which I don't know if I want to get too deep into, but essentially telomeres are at the ends of our DNA. They're just a bunch of like copies of random ass things that don't really code for anything, but they're there almost as like a buffer so that when the DNA gets duplicated, if in case not all of the DNA gets duplicated and it gets cut short, the part that gets cut off at the end is the telomere, which doesn't code for anything. So it's almost like a protective end of the DNA. And there's a theory that every time the DNA replicates, this telomere gets shorter and shorter and shorter until it disappears after a certain amount of replications. And then if it disappears and then the DNA tries to duplicate again and the telomere is gone, then it will cut into the actual useful DNA, which can then cause problems within the cell and so on. And then one last thing that I'll note is that although I also should probably have highlighted this a little bit more specifically, but these are all like hypotheses, right? These are not like, this is absolutely what happens as you age. These reactive oxygen species are definitely going to cause damage to your DNA. These reactive oxygen species are going to puncture holes in your cell membranes and your cells are going to die. No, these are just theories at this point. The telomere, I think, is a little bit better established, but there's still things that aren't known about it because telomere length doesn't really predict life expectancy. So, like, for example, I'm pretty sure mice have longer telomeres than humans, but mice have a shorter lifespan than humans, right? So it's like, it doesn't really define how much time you have on this earth, right? So there are things that are not as well established or understood. But one thing that is useful in understanding aging is that there are a lot of disorders when it comes to aging. There are instances where people age at a much faster rate. So like children will get gray hair or something like that. And then you can like look at those people's genomes to see what's different. And if there are certain genes that are overexpressed or create more protein, that could be contributing to aging faster than other people. Or the opposite, right? So still lots left to learn. But overall, these are sort of the working hypotheses as to what contributes to aging on a cellular level. So that's that. That's question one. What causes aging? I'm going to take a sip of my latte. I think you can hear my voice is cranky. Okay. So the next question that I am asking today is, why is my hair turning gray? And I'm assuming here, again, emphasizing that this is not a podcast for children. Not that there's anything inappropriate, just that I swear too much. But I assume that a lot of people who listen to this are like close to my age. So maybe you, like me, are experiencing gray hair growth in your late 20s, early 30s. I found my first gray hair when I was in grad school. And I remember I plucked it. And I was like, I wanted to burn it. I was like, I need this to go. I think I was like 24, 25 maybe. And then every now and then I would like see one and pluck them. And then I stopped plucking them because I was like, if I keep plucking them, I'm going to have no hair left on my head. So I now just let them grow. I embrace them. But I still wonder, why is this happening? Like, what's going on? What's happening to me? Not in like a dramatic way of like, oh, life is hard. But like, I'm just like, what the hell? My hair is very dark brown. Black, maybe. No, I think it's more dark brown. I don't know. But, and then they have these like random ass white hairs that just like pop out of nowhere. It's like, where did that come from? Why is that happening? So this question really addresses why gray hair happens and where it comes from. But before we dive into gray hair specifically, I kind of want to give a primer on hair in general. So, as you may be aware, hair does indeed grow out of our skin. And skin, which we actually just talked about a few weeks ago. So our hair grows out of hair follicles, or like a root that is planted in the dermal layer of our skin, so the dermis. Remember that Barbie layer that has all the blood vessels, all the sweat glands, all the fun stuff? It also has hair follicles. And new hair cells are created in the follicle, and it pushes the old hair cells out. So kind of like when we were talking about the epidermis and how new cells are built in the basal layer and then it gets pushed up. Sorry if you didn't watch last time's episode, but we talked about skin and we talked about how new cells are created and pushes the old cells up and out. The hair follicle does the same thing. So all of the hair, like the hair that's furthest from your head, the hair that's all the way at the bottom, like this is the oldest hair. And the newest is the one that's like coming right out of your head. I don't know why I had to take my hair out of my clip to show you that, but there you go. So that's similar to our skin, right? Where like new hair cells push old ones out, and then the ones that are out, the furthest out, are the oldest. Also, just like our skin, there are melanocytes that are near our hair strands in the follicle, and those create and deposit melanin, which make our hair pigmented. And there are different melanins and different proteins for different hair colors. So I think for like darker hair, like black hair and brown hair, there's eumelanins. And then for like red hair and blonde hair, there are pheomelanins. But essentially what they are just proteins that provide pigment to your hair. So when there's no pigment in your hair, so there's no eumelanin, there's no pheomelanin, it will just be white or gray, non-pigmented. And that means that there's no type of melanin in your hair, or no pigment, no melanin deposited into your hair. So that's a little background on hair. But the real question that I wanted to ask is, why is this happening? Like, why is my hair turning gray? And thanks to the review article by Joe and colleagues, which is linked underneath, of course, I forgot to mention, but as always, the sources are linked below in the episode description. But thanks to a review article, I now know 3 potential mechanisms for which hair turns gray. So I'm going to walk through each of the hypotheses with you here so that you may also now know why hair turns gray, potentially. These are, again, hypotheses, potential possible mechanisms for why hair turns gray. So one hypothesis is that oxidative stress impacts the hair follicle directly. So again, we're getting back to this idea of oxidative damage and oxidative stress. And here, thinking about, again, those reactive oxygen species, those ROSs that we talked about earlier, they can cause stress and damage to the melanocytes that are in the hair follicle and the cells in the hair bulb. So those melanocytes are the cells that make melanin and deposit that pigment into the hair. And if those melanocytes are damaged by reactive oxygen species, then they're not going to be able to do their job, which means that they won't be able to deposit pigment into your hair, which means that your hair will be non-pigmented, which means that your hair will be white. That's the first hypothesis. It can be caused by inflammation, UV light, psycho-emotional stress, cigarette smoking, or other chemical or genetic damage or causes. I think that makes sense to me because I mentioned my first gray hair was when I was in grad school. Grad school, stressful. Don't know if you've ever been. Stressful. So I think that checks out. Anecdotally, I agree with that statement. Although it's interesting because they say UV light in a lot of these, but then there was a sentence in the paper that's like, well, we looked and that, well, not that they looked, but they said like farmers don't gray faster than office workers, which I think is an interesting thing to explore further, because if UV light really does cause gray hair, if UV light does, yeah, again, English first and only language. But if UV light does cause gray hair, then you would expect farmers who are like outside all day to have gray hair, or get gray hair faster than somebody who works inside all day. So that's an interesting study. Anyway, Sam, come on. So essentially, the first hypothesis here is that the melanocytes that are at the very base of the hair follicle, or the hair strand, they are impaired. They don't properly deposit the pigment into the hair strand. No pigment, no color, white hair. Womp, womp, womp. Okay. A second hypothesis into why hair turns gray is that there is a defect in the self-maintenance of melanocyte stem cells. So stem cells might be a term that you've heard before. They're essentially cells that are undifferentiated. And that means that they're cells that have the capability of turning into another cell, but they haven't matured to that point yet. They haven't turned into that cell fully yet. So melanocyte stem cells are cells that will eventually turn into melanocytes, but they're not quite there yet. And the maintenance of these stem cells is important to make sure that they develop properly into melanocytes. And the maintenance of these cells relies on cellular mechanisms involving BCL2, which is something that regulates apoptosis, which is also known as cell death, or programmed cell death. The cellular mechanisms for maintaining these stem cells also include MIT-F, TGF-beta, and collagen 17A, which are essentially just additional factors to make sure that this stem cell grows properly and turns into a melanocyte properly. That's the big picture there. There are studies that investigate the role of these factors specifically for melanocyte stem cell differentiation, which I think is the technical term, but essentially making sure that these melanocyte stem cells grow into melanocytes. A lot of the studies that support that hypothesis have been done in mice. So, for example, the review paper talks about a study in mice that have insufficient collagen 17A1. And in these mice that don't have a lot of this collagen, they found premature graying and hair loss. So essentially, kind of working backwards from that, the presence of collagen 17A1 does contribute to what's the opposite of premature graying? On-time graying. Punctual gray hair. But essentially, like when mice don't have this collagen, they gray sooner. They gray faster. So it essentially means that collagen 17A1, which is related to melanocyte stem cell regulation, also has an impact on gray hair. So those two are kind of tied together. Another study looked at BCL2, which BCL2 is a factor that regulates programmed cell death or apoptosis. And when they found that when BCL2 is unregulated, meaning that it's not kept into check and cells die off because the BCL2 is supposed to turn on when cells are supposed to die and turn off when they're not supposed to die. But if it's unregulated and it turns on, the cell will die. And they found that BCL2 deficiency also leads to a loss of these melanocyte stem cells. So showing that BCL2 plays a big important role specifically for melanocyte stem cells. So MIT-F, which is, not that you need to know this, but the microophthalmia associated transcription factor. Okay. But MIT-F is important for melanogenesis, so the development of melanin. And it plays an important role in pigmentation during the differentiation of melanocyte stem cells. So when MIT-F is dysfunctional, the melanocyte stem cell does not mature properly and does not properly create pigment. And when the melanocyte stem cell doesn't mature properly, it doesn't turn into melanocytes. And then if it doesn't turn into melanocytes, then it doesn't produce melanin and deposit pigment into the hair, which is sort of like all individually coming together to say that melanocyte stem cells are important for normal, healthy melanin. And then if there is no normal, healthy melanin in the hair, then there won't be any pigment in the hair, which means that it'll be white or gray. So that's the second hypothesis there. A third hypothesis as to why hair could turn gray is also impacting the melanocyte stem cells, but there's a theory that active hair growth could be causing this, or could lead to a chain reaction that causes issues with melanocyte stem cells. So the theory here is that as hair grows, as I mentioned, hair grows from the root, from the base, and it pushes old hair out. So as hair grows, the cells are dividing. So they're like multiplying their DNA and splitting and all that stuff, but that requires energy. And as I mentioned earlier in the episode, we use metabolism of glucose to make energy. So when hair grows, it requires a lot of energy to be made, and then that energy is then consumed. So there's an increase in metabolic activity when hair is growing. And as we know, when there's an increase in metabolic activity, there's an increased risk for reactive oxygen species to be created. And when reactive oxygen species exist, there's an increased risk for damage. So the theory here is that as the hair cells are multiplying and the hair is growing, it's creating these reactive oxygen species as a result of increased metabolism. And then those reactive oxygen species are then causing damage to the melanocyte stem cells. And then those melanocyte stem cells are dysfunctional because they're damaged by the ROS. And then they, in turn, don't do their job. They don't turn into melanocytes. They don't make melanin. They don't deposit the melanin into the hair. And then you get unpigmented white hair. So it's almost like a catch-22. Well, not a catch-22, I guess. But it's like the hair growth. It's like the graying hair is an actual result of the hair growth, which just doesn't seem fair to me personally. But what in life is fair? Not much, tragically. So that's the third hypothesis. I thought that one was interesting, unfair, but I get it. I understand. I think it actually kind of helps too. My understanding is just like, oh, it's literally just hair that doesn't have pigment in it. It's not that big of a deal. Like, it's fine. It made it a little easier for me to accept my grays when I understood what was causing it. It's just like, oh, it's just time. There's nothing really we can do. It just happens. I mean, you could dye your hair, not dye. Jesus Christ, Sam. You could dye your hair. I'm not going to dye my hair. I've done it a few times. Every time I've dyed my hair, I've been like, why did I do that? I mean, if you dye your hair, God bless. But for me, when I look at my hair, I think I'm just so used to having my natural hair that when I tried to dye it and get like highlights or something, I'm like, what the fuck am I doing? I've hated it every time. So never again. Anyway, I'm going to embrace my grays. I think they're hidden pretty well on the camera, but I'm going to embrace them. I'm just going to let them hang out, whatever. If it gets to be too much, I'll ask them to pay rent. We'll see. But yeah, overall, why does hair turn gray? The melanin in our melanocytes is not produced, doesn't get deposited into our hair, and then in turn, our hair just grows in unpigmented or white. Life happens. Hooray. Every day above ground is a great day. Remember that. Pitbull. Okay, here are the takeaways for today's episode. The processes of life make us older. Aging is a consequence of time. And the processes of life make us older. What are you going to do? We don't really have a choice, I think, is the point that I'm taking away from this, is that we really don't have a choice. And all you can do is just keep on living. Get busy living or get busy aging. Either way, well, both will happen. Aging will happen whether you want it to or not, is what I took away from this. Another takeaway that I guess I didn't really show science for, but our collective human life expectancy increases as we get better at like identifying and treating diseases. But even with that, aging still happens, right? So eventually we all age, right? There were times where like I guess the flu does still kill people. So maybe that's not a good example. But there were like, back in the day, there were like diseases that like could kill people. There still are. But like now we're like, oh, we just vaccinate, or we have like an antibiotic or an antiviral or whatever that can like prevent somebody from dying from something that is now preventable. And that in turn increases our life expectancy. But even if we don't die from a preventable disease, we're still aging and we're still gonna die eventually. I fear this is not as motivating as I was hoping it would be. But you know what? I am not here to be an optimist. I'm here to be a realist. Sorry if it's harsh, but we're all going to die one day. It's part of life. Death is a part of life. I was going to say life is a part of death. Maybe that too. I don't know. I've never died before. Anyway, the last takeaway from this episode is that gray hair happens. The exact reason as to why it happens is not totally well understood. But it's inevitable. So you can own it or you can dye it. Or I think that really those are the only two options, realistically speaking. At least that I see. Those are the only two options. So I'm going to own it. You do you. Okay. Why is this episode such a hot mess? Okay. Chaotic as hell. You know what the issue with me is? And I guess maybe I'm like, I want to say I'm a perfectionist, but perfectionism is the enemy of progress. So I'm like, this episode is bad. I'm not going to put it out, or I'm going to re-record it. And then I just end up re-recording it like 4 times. And it's like, who's got the time for that? So sorry if this episode was bad. I hope you enjoyed it. I hope you learned a little something. I hope it wasn't chaotic as hell. I feel like recording it felt chaotic. I think I'm going to edit it back and be like, this was awful. But it's going to go out because I need to put something out. Because I told myself I would, so I have to. So if this is bad, I'm sorry. And maybe next week will be better. Or next time will be better. No promises. But thank you for watching. I hope you enjoyed the chaos. Please don't forget to follow, rate, and review the podcast wherever you listen. You can also subscribe on YouTube, please. You can follow the show at Sam-Splaining Sci on Instagram, Twitter, and TikTok. And you can connect with me there and ask questions if you'd like. You can also ask questions at samsplainingscience.com/ask. So if you have anything that you want Sam-Splained to you, ask away. Thank you again for listening to this week's episode. I'm sorry it was chaotic, but progress, not perfection, right? Right? But yeah, I hope you learned a little bit and I hope you laughed a little bit, and I will talk to you next time. Ciao for now. Bye.